Welcome back to your favorite class of all time. Today we're going to talk about the normal curve and the empirical rule. All right, so what is the normal distribution? Many populations of quantitative data seem to fall in what's called a normal or bell-shaped distribution. The bell-shaped curve is exactly what you probably would guess that it looks like. Something like this, where the mode is right in the middle here. And we also say that the mean is the same as the mode. So the mean and the mode are the same, excuse me. The mean and the mode are the same in the normal distribution. So if this is what we call x bar, the mean, then half of the data, or approximately half the data, fall below the mean, and half of the data fall above the mean. So we can come up with many examples in real life of the normal distribution. It is bell-shaped, as I mentioned, and it's symmetric. So the area to the left of the mean is equal to the area to the right. It doesn't look like it on my picture, but and then as we go further and further to the left and further to the right, we get a few outlying values, but most of the data tends to fall in, this bulk here. So the bell shape is not, every single normal curve is not exactly the same. There are many different shapes and sizes of the bell shapes. So here's a couple of examples. Remember that mu means the population mean, right? So the population mean here is 9, and the standard deviation is 2. So that means that if I add 2 to 9, this data falls within 1 standard deviation above the mean. This data falls within 1 standard deviation below. This would be another standard deviation above, so 13 is 2 standard deviations above the mean. 5 is 2 standard deviations below the mean, and so on. Here we have the mean of 3, standard deviation of a half, the mean of -2, standard deviation of 1. Keep in mind that negative numbers do come into play sometimes. For example, temperatures, altitudes, debt, things like that. So negative numbers can be data lists. You can have data lists with negative numbers. So notice what happens when we have a small standard deviation. It tends to bunch up around the middle. And when the standard deviation is relatively larger, it tends to be a little bit more, spread out like this one is. As you can see, the mean and the standard deviation determine the shape of the bell curve. So we talked about that. The shape of the bell curve is largely and completely determined by the mean and the standard deviation, which of course are determined by the data itself. So some examples of normal distributions. Specifically, if I collect data from samples of people or animals or whatever that fit these descriptions, what you will find is that when you make dot plots or histograms of these data, it'll sort of follow that bell curve that we had talked about earlier. So when we're going through each of these examples, I want you to think about this question. What would the mean be, or near, and what would the standard deviation be for each variable? So a good example of this is test scores. Test scores, let's say out of 100%, right? So if 100% is the maximum test score, and a statistics class takes an exam, let's say it's not the particularly easy exam, but it's not the hardest exam ever. You could think about what would be the average test score, what could be the average test score. And then also what would the standard deviation be for that list. And of course this varies, but an example of a mean could be 70%. It could be 75. In my calculus class the other day we had a mean of 84%. So this particular calculus class is performing at a little bit higher level than some of the other ones that I've had in the past. And that happens sometimes. I'd like to think that, that's partially because of me, but I don't want to think too much of myself. Anyway, and then the standard deviation, you can think about, what could the standard deviation be? Well, in this case, if the maximum score is 100, if the maximum score is 100% and the mean is 70, then you can think about, well, if the data is pretty well spread out, then the standard deviation is going to be larger. But if the mean is 75 and the maximum is 85 and the minimum is 65, it's pretty well bunched up around the middle. So it's all going to depend on that class or that set of data. All right, so here's some health examples. Heights and weights separately of clinic patients. So what you want to do here is you don't want to include everybody in the same population or the same sample. You would want to separate men from women, and you would also want to separate them from children as well, because you wouldn't want to compare the height of a child to the height of a full-grown man. That doesn't make any sense. So you might say, okay, well, of my clinic patients, for men aged 18 to 30, what is the average height? What is the standard deviation of the heights? What is the average weight of women who are in Weight Watchers who are aged, 20 to 45, whatever, So you find a category and then you can think about heights and weights. So again, ask yourself, what do you think the mean height for men, or let's say 10-year-old children, or 20 to 45-year-old women? What's the mean weight of each of these people in pounds or kilograms? Another example, IQ scores. Think about what you think the average IQ score is and what is the standard deviation. Shoe sizes. What's the average? Maybe what's the average for men? Again, what's the average for women? And what's the average for 10-year-olds? Again, you want to be specific because you don't want to be comparing the shoe size of a baby to the shoe size of a man. That's pointless, right? You know that the man's going to be larger in just about every example, or every example, hopefully. Standardized nursing exam scores. Pregnancy duration. We would expect the mean to be how many months, or maybe how many weeks, and then the standard deviation. Obviously, not every woman has exactly the same number of days or same number of weeks in her term, in her pregnancy. So what's the average and what's the standard deviation? This I don't know, but it does exist. Okay. BMI, body mass index, is that what that stands for? Yeah. So what's the average? You can come up with all kinds of examples for these. So some properties of a normal distribution. Again, symmetric and bell-shaped, and it's completely determined by its mean and standard deviation here, which again are in turn determined by the data itself. Okay. The total area under the curve equals 1. All right, I want to talk about this a little bit. So this is the real number line, and this is the curve that we're referring to. I'm drawing it the best I can. It's not perfect. But anyway, when we say area under the curve, we mean this. And I can call that A, right? The total area is 1. Okay? So you can think about, if I cut that and if I slice that in half, what area goes here? That's right, 50%, or 1/2, right? And what area goes here is another half, 50%. The x-axis, which is the horizontal axis, is a horizontal asymptote for a normal curve. Without getting into a lot of detail, a horizontal asymptote is a horizontal line for which the curve sort of gets close to that value. So these heights, once again, those are frequencies or relative frequencies, right? So that as, let's say if we're talking about a mean exam score of 75 5%, right? Hopefully it's clear that, there is a absolute minimum of 0, but maybe 0 is way out here, in no man's land. Maybe the lowest score on the exam is 30. So the point is that as you get closer to 0 out going this way, there's going to be fewer and fewer students who score in that. And if you've ever seen distributions of scores, you know that's true. Usually I'll get 1 or 2 that score dismally, and most people score usually, in this range somewhere. So, an example, a Western college has an enrollment of 3,264 female students. Records show that the mean heights of these women is 64.4 inches, okay, with a standard deviation of 2.4. The data collected is displayed in the table below. So hopefully you can read that. We've got heights here. We've got relative frequencies in this part of the table, and frequencies, and then relative frequencies here. So once again, remember what frequencies mean? Frequencies means counts for those categories. So here the category is, it says, I don't know if you can see it, but it says 56 less than 57. And what that really means is the height of the lady is between 56 and 57 inches, which on the number line, of course, means if this is 56 and this is 57, remember that height is a distance, and so even though we may measure it in half an inch, quarter inches, eighths of an inch, and so on, you can actually have what's called continuous, so if you have a continuous data, so if you have a measuring device that has very, very small increments, you could measure it all the way down to the 100th of an inch or 100th of a millimeter. So the point is that any woman that falls in that category counts as one of those 3 women. So think about 56 inches. If you convert that to height, what is that? That's 4 feet. And say 48, so that would be 8 inches, wouldn't it? 60 inches would be 5 feet. You can check that. Anyway, so there aren't that many of them out of 3,000 women, 3,200. There aren't that many of them that are that short. Okay, and then of course the bulk are centered around 64 inches, which is about 5'4" to 5'5", which is probably what you would expect. Okay, and again, 64.4, that would be 5 feet and 4.4 inches. Right, so that sounds about right for the average height of women, and that could be a specific college, that could be United States, that could be the world, right? In this case, they're specifying colleges, or this particular college, that is. Maybe it's UCLA. And then if I was to draw a histogram, you'll see that the midpoints of these bars follow this normal curve that goes all the way up to the mode and then all the way back down. Hardly anyone or no one is shorter than 4 feet 8, and hardly anyone is taller than 73 or 74 inches, which remember, that's, what is that, 6 feet 1. Almost no women are taller than 6 feet or 6 feet 1 inch. There's a few in the WNBA, but these are college people. So anyway, gives you a little idea of a normal distribution. As you can see, the data falls into an approximately normal distribution. It's not perfect, but it's good enough. So if you have enough data, in this case a huge amount of respondents, what you will find is that it'll either happen to this, or if you calculate the sample means, you can put the sample means in what's called a normal distribution. So later on we're going to learn about that. Okay. In general, if you have a normal curve or an approximately normal curve, you can assume the following rule. This is called the empirical rule, or the standard deviation rule, right? About 68% of the population falls within one standard deviation. I want to be clear what we mean when we say within one, right? Within one. So again, if the mean is here, right? Let's say that, just for the sake of it, that the S is 2, right? The standard deviation is 2. Then one standard deviation above the mean would be x bar plus S, and one standard deviation below the mean would be x bar minus S, or x bar minus 2. So what we're saying is that this area is encompassed by 68% of all the data values. So most, more than half. 95% is within 2, so this would be x bar minus 4, x bar plus 4. So if I add those two areas, I now have 95% of the overall. And finally, if I go another standard deviation up and down, this would be x bar minus 6 and x bar plus 6, right? Excuse me. If I add these two, now I've got 99.7, or almost all of the data. So the examples of outliers I used up here and down here were WNBA players for women, WNBA, right? And here maybe little people, people who have a dwarfism, they are born in such a way that when they grow up, their growth is stagnated, so they don't grow up to be as tall as the general population. All right, so here is a normal distribution. So think about which of the examples we looked at earlier fits this one. In other words, the mean, I'm going to call this mu, right, instead of x bar. The mean is 100. If you guessed IQ scores, you guessed right. All right, mean of 100, standard deviation of 16. So if you know that your IQ is 116, now you know that you are one standard deviation above the mean, right? So we can ask questions based on this information using the empirical rule, all right, or standard deviation rule. What percent of the population have IQ scores below 84? So identify where 84 is. So this would be below 84. Okay? So based on what we did here, keeping in mind that 68% fall within 1, 95 within 2, and 99.7 within 3, you could answer this question. So you know that this particular amount here, this area, is 68%, right? And you know that 95% is encompassed by two standard deviations within 2 standard deviations of the mean, right? So that's 95, and then 99.7 for the rest, right? So in order to determine this region, call it A, right? You would have to ask yourself, well, what is the complete area of this red portion, right? Call it B. Well, if you know that it's symmetric, right, then you know that 50% of all the values, including these, right, 50% of all the values are less than the mean, right? And so if I'm trying to figure out from this point to the left, in other words, all of this area in section A, I would need to figure out what B is so that I can calculate it. So A plus B is 50%. Agreed? 50% total, right? Remember that percent as a decimal, we move the decimal 2 spaces to the left, so 0.5. So to calculate A, doing a little bit of algebra here, right? A is 0.5 minus B. So then the question is, well, what's B? Well, if 68% is both of these sections, then B is going to be half of that. So that's 34%. So A is going to be 16% of the overall data. So there's the 16% here. What percent of the population have IQ scores below 116? Let me see if I can do a little bit of erasing here. Okay, we'll start over. So below 116 would be all of this. So again, if you cut that and you realize that's 34% and that's 50% there, you would add that together to get how much? So again, if I call that area, let's say C, all of that, right? That would be 84%. This is incorrect. It's 84%. Because obviously it's more than half, right? And what percent of the population have IQ scores between 84 and 116? So between 84 and 116, I think we answered that already, because this is one standard deviation below the mean, right? Because 100 minus one standard deviation, right, is 84. So that's where the 84 comes from. So this is mu minus s, this is mu plus s, and so on, mu plus 2s, mu minus 2s, right? So we know that this is, from the empirical rule, how much? That's right, 68%. What percent of the population have IQ scores between 84 and 132? We'll just tack on another one of those, right? So let's erase a little bit to clean up. So I know this is 68%, right? And I know that if I add on both of these, I get a total of 95. So if I subtract 68 from 95, what do I get? 27? Which means that both of these account for 27%. So 13.5% here and 13.5% here. Because if I divide that by 2, that's what I get, 13.5. So then if I take the 13.5% and add it to the 68%, that will give me the answer to this question, right? So 68 plus 13.5 is 81.5%. This concludes the slides. Have a great day.